Welcome to ELET B70 Mechanical Systems. This is your professor, Roy Allard.
In this lecture, we'll be discussing gear drive systems. We'll be reviewing gear terms and fundamentals, different types of gears, enclosed gear drive types and terminology, and then finish up with common gearbox configurations. Just as we've discussed in belt drive systems and chain drive systems, we're going to have a driver gear and a driven gear. The driver gear is the gear that is attached to the movement device, and the driven gear gets moved by the driver gear. In gear systems, it doesn't matter whether the driver or the driven gear is larger or smaller. It's the smaller gear of those two which is called the pinion. So the pinion is the small gear in a gear set. Then the other gear is just simply called a gear. The next thing we need to discuss on this slide is the presence of what is called an idler gear. So let's take this illustration for example. Since this is the driver, and if it is turning clockwise, as the gear teeth mesh, it's going to turn the driven counterclockwise. So in a two-gear set, we will always have an opposite rotation from the driver to the driven. Now let's look at this illustration down here. When we put an idler in the middle, here's our driver spinning clockwise, which turns the idler gear counterclockwise, which then turns our driven gear clockwise. So with the addition of the idler gear, we can actually cause both the pinion and the gear to rotate in the same direction. Remember, on the last slide, we talked about the smaller gear in a gear set is called the pinion. So just like the small pulley or the small sprocket, it is going to spin or rotate faster, and it's actually going to do more work. Let's look at this set for example. This is the driver, so the motor is attached here, and it's applying power to the driven or the load. Now this is the pinion gear because it's the smaller gear. Again, it doesn't matter whether it's on the driven or on the driver. We have 60 teeth on the driver gear and 30 teeth on the driven gear. So this pinion will work twice as hard. Each time its teeth mesh twice, the gear is only going to mesh once. So you can see it is working more. The teeth are in contact a lot more, and it is going to be rotating faster because of the number of teeth on the gear. So we have to make the pinion for a gear set to be a tougher material because we want to keep it from wearing out. So let's look at this. We've talked about this. This is a review from the lecture previously on chain drive systems where we talked about speed increasers and speed reducers. So when the driver is smaller than the driven, we have a speed reducer. And we can simply just look at this. This is going to have to go around several times before this goes around once, because each one of these teeth of the gear are going to mesh at a time. It's almost easier to see in a gear drive system than a belt and a chain drive system, but the principle is exactly the same. And then when we have the larger gear being the drive gear, we call it a speed increaser. So as this spins around once, 60 teeth are going to engage. So it's going to engage 60 teeth of the driven gear. But there are only 30 teeth on this gear, so this gear will have to spin twice as fast to engage the same 60 teeth. It'll spin around twice for each revolution of this drive gear. So we call that a speed increaser. And just like we talked about last lecture, if we have a speed increaser, what is our output torque going to do in relationship to our effort torque? Well, you're right. The torque is going to decrease. Remember, speed and torque have an inverse relationship. If the speed is going to increase, then the torque is going to decrease. On a speed reducer, if the speed reduces from our effort to our load, then our torque is going to increase. There's a great video that I want you to watch. There are 2 parts to it. It's in this week's videos, and it talks about a manual transmission. If you don't know how a manual transmission works, please watch that video. It'll really bring it to light as the person explains the ratios and how we're meshing the gears. And you'll actually see, you can physically see the size of the gears. So if you just sit and look at the gearbox, you can tell what first gear will be, because it will be a speed reducer and a torque increaser. And then as we increase those gear sizes are going to be closer to the same size. When we have a gear with the same number of teeth on both sides, then we have the same speed from the input to the output and the same torque. We don't need that high torque. Once that vehicle is moving, or we can put this into industry, once that machine is moving and up to speed, we don't need the torque that is going to be supplied by a speed reducer and a torque increaser. So as we shift those gears in a manual transmission in an automobile, our torque goes down every gear we go up. And you'll actually see that relationship. So watch that video in this week's video section. For gear systems today, the involute gear profile is the most commonly used system. The profiles of the teeth are in an involute circle. So this is what we're talking, this involute circle right here. From this point A of the root circle of the base of the gear, and it's coming off. So it's like the spiraling curve traced by the end of an imaginary taut string. This being the taut string here, unwinding itself from the stationary circle called the base. And this is the base right here. So that gives us this rounded, curved tooth profile, which we call an involute. So with that involute gear profile and the design of the teeth, the contact between a pair of teeth occurs at a single instantaneous point. Here's the point right here. Let me put this in motion for you. Watch how the contact between the teeth starts and moves along because of the involute curved profile of each tooth. So here you can see the taut string unrolling from the base circle right here, this blue line. And that's the involute gear profile in action. You can actually see how the teeth mesh. And so now you can understand why it's so important for that smaller pinion to be much stronger, because that tooth has a lot of pressure. And they're going to be used much more often because there's a less number of teeth in the pinion gear than in the other main gear or wheel, as it's called. The next term is called the pressure angle. It's the angle at which the pitch point between the line of pressure, which is normal to the tooth surface, and the plane tangent to the pitch surface. So you can see it's kind of like the slant of this tooth. Standard values of the pressure angle are 14.5, 20, and 25 degrees. Now your book talks about 20 being the most common now, and it is. This is important to know the pressure angle because gears of different pressure angles are not interchangeable. The gear teeth will not mesh properly and it will cause damage. If this pressure angle is greater, then the meshing is going to be harsh. And in some conditions, it will lock up that gear set and prevent it from moving and cause damage to the system, the bearings, the shaft, and even the motor and drive system. So be sure you're using gears of the same pressure angle. This pressure angle actually determines the shape of the tooth, because with a different angle, the shape will change because of this angle and the slant of the tooth. So the shape of the tooth is determined by that pressure angle on the previous slide. But the size of the tooth, how big it is, how large it is commonly determined by the diametral pitch. The diametral pitch is defined as the ratio of the number of teeth for each inch of pitch diameter of the gear. So it might seem like a complicated definition, but in the next slide we'll show you how simple it really is. So to understand diametral pitch, we need to know the pitch diameter. The pitch diameter is determined by the point on the tooth at which force is applied to rotate a gear. So you see this imaginary circle going through the middle of the teeth? That will be the circle that we measure the pitch diameter. So we don't go to the very tip, we don't go to the very root or valley. We kind of take it midway. That's the point where the force is applied. We actually saw that force moving along the gear tooth in the involute profile graphic image. So because this pitch diameter occurs around the circumference is pi, or 3.14159. Oh, it defines it as 1416 down here. That's where we're rounding. Then it's the number of teeth per inch of pitch diameter. So this gear is actually a 5 diametral pitch with 48 teeth. But let's go on to the next slide to clear things up a little bit. So to find that diametral pitch of 5 with those 48 teeth, we actually measure here and we get 9.6 inches. So to calculate it, we have 9.6 inches and 48 teeth. So we divide the number of teeth, 48, by the diameter, which is 9.6, and we get a 5. So 5 is the diametral pitch, and it's that easy to calculate. But what this means is that the pitch circle circumference is 9.6 times pi. That's the circumference, which is 30.16 inches. That's the circumference of this imaginary line going through the middle of the teeth. So there are actually 48 teeth through the entire 30.16 inches. So for every 3.14, there will be 5 teeth. But this can be very complicating to figure out. So it's easier just to take the number of teeth divided by the pitch diameter. Now, it's critical that we match the diametral pitch of gears. We can't take a diametral pitch of 5 and mesh it with a gear with a different diametral pitch. Because for every inch of movement on that gear, there's going to be a different number of teeth meshing. So that will cause a very big problem. In this case, for every 3.14 inches of that circumference going around, 5 teeth are going to mesh. Now, if we had a different diametral pitch, say of 3, that means for every 3.14 inches, we would only have 3 teeth meshing. Well, there's no way you could have 2 gears with different diametral pitches, 3 teeth and 5 teeth, for the same amount of movement and have them mesh. So matching that is very important. And with a big difference in diametral pitch, you can just hold the gears and try to push them together by hand and turn them without being on the shaft, and you'll totally recognize that they won't turn at all because the teeth don't even line up and mesh. We've hit on some of the main terms of gears, but there are several more, and we need to talk about the important ones. First is clearance. It's defined as the distance between the top of the tooth of one gear and the bottom of the meshing tooth of the other gear. So it's kind of hard to see, but you can see where this space is right here. So this is the top of this tooth and the bottom of this one, and they're going to mesh. And here they're totally meshed because everything is in line, and there's a little clearance between the top of the tooth and the valley of this area. So that is called clearance. So it's the top of the tooth right here to where it fits into the other tooth. Okay? And there's not going to be a tooth that's going to fit all the way down to the bottom, because if it did, it would cause a binding action. So we actually have to have this clearance so the teeth will mesh and not bind. There's only so much space here. These shafts are not meant to bend outward. And if these tooth didn't have the clearance in here, then we would put stress in this direction on this shaft and in this direction on that shaft. It'd want to push them apart. So that's what clearance is. Backlash is a similar clearance. It's just between the sides of the gear tooth when those two teeth mesh. So it's the side to side clearance. That's called backlash. We need to have that clearance on the sides because the teeth would be so tight fitting together that it would cause undue stress and a lot of friction and a lot of heat and premature failure. So proper clearance between the top and the bottom and proper backlash between the sides is very important. Now your textbook contains more information on some various terms. So definitely read through that and use that along with this PowerPoint lecture to help complete your homework for the week. Now we're moving on to talk about the different types of gears. So the first type we're going to discuss are the spur gears. All of the gears that we've been using as examples to go over the terms and definitions have been spur gears. Spur gears are the original gear type. Their teeth are involute, as we've already talked about. Because no more than two sets of teeth are in contact at any one time, the load is transferred pretty abruptly from the drive to the driven, or from the pinion to the gear. So spur gears have more noise and more vibration than other gear types that we'll be discussing later in this lecture. There are three configurations of spur gears. External drive, which this is an example of an external drive. So both the pinion and the gear have their teeth on the outside of the wheels. So this is an external drive. And then we have an internal drive. So you can see the pinion has its teeth on the outside, but the gear has its teeth on the inside. So this is called an internal gear set. The third configuration of spur gears is rack and pinion, and we'll show that example in a few slides. So with an external gear, we can use them to increase speed, increase and decrease torque, and the two gears in the gear set, the gear and the pinion, spin in opposite directions. We discussed that. If this is spinning clockwise, the pinion, then the gear is going to spin counterclockwise. Now with an external or an internal gear, they're going to turn the same direction. So if the spur gear is spinning clockwise, as it meshes to the internal gear, this red is the pinion spinning clockwise, and you can see it's going to spin the yellow clockwise. So these internal gear sets have external teeth on one of the gears and internal teeth on the other. As you can see, the shaft distance is much farther apart on an external gear drive system, where they're much closer on an internal gear set. The tooth strength is greater and the shaft distances are much closer, as I pointed out on the previous slide. With an internal gear set, both drive shafts will rotate in the same direction, as I also pointed out, and not like opposite directions with a standard external set with no idler. We would need an idler, and we would separate those shafts even further than they were on the previous slide. So a planetary gear set is another form of internal gear set. It's similar to an internal gear set, but it has additional gears inside. Planetary or epicyclic gears are used to transmit power. I remember several years back, the snowcat from the Forest Service broke down, and we went in to help change the planetary. So the snowcat has two planetaries, one on the back of each track. And the planetary gear is connected to the cogs that actually move the track to make the snowcat go. It had to be taken out, rebuilt, and then we helped them put it back on. So power transmission such as snowcats and Caterpillar tractors and other heavy equipment. Because they have the idler gears, both shafts rotate in opposite direction. You can see we have these two gears in here, and we've centered the spur gear in the center of those two gears. So you can see if our spur gear is rotating clockwise, it will rotate these idlers counterclockwise, which then rotate the gear, the external gear, or the most outside gear. It's actually an internal gear. The internal gear, the larger one, will be spinning clockwise as well. So counterclockwise on power, if this is the drive, and then the driven is going to spin in the opposite direction. So depending on the mechanical machine and the device, we may have just the two gears and spinning in the same direction with offset shafts. So a motor would be attached to this side coming out of this red end. And then whatever we're spinning would be attached to the back side of the spur gear going this way. And so you can see those two shafts would be slightly offset. Where these are centered, one's in the center, and it would be connected on this side, driving from the other side of this red internal gear coming out this way. There's another gear set that uses multiple gears, and it's in the differential of a vehicle. With a differential, it allows power to be transmitted to the drive wheels. So there is a pinion gear that is offset on the end of the drive shaft, spinning in this direction. The pinion is not actually shown here. It would be spinning and turning this big ring gear on this carrier that's holding the other gears. So let's look at this. Input torque is applied to the ring gear. So that's going to be applied from the drive shaft through another gear that's going to mesh with this. So this ring gear turns the entire carrier, this whole blue section, providing torque to both side gears, this yellow and the red. So these would be the axles going to your wheels. If resistance at both wheels is equal, then this green gear, called a planet gear, does not rotate, and both wheels turn at the same rate. Well, that's great, but both wheels of a car don't always turn at the same rate. What if we encounter some resistance, or we're actually turning When we turn, we're going to encounter that resistance. For example, when we turn to the left, this is going to turn much slower than the right side of the vehicle because it has a lot more ground to make up. So if the red side, the left side over here, encounters resistance, the planet gear here will rotate. And it turns and applies extra rotation to the yellow gear on the right side. And that's the basic function, how gears are used in a differential of a vehicle. Now there's a lot of different types of differentials. Some can lock the axles together, such as in a locking differential. Some have clutches in here to help keep them from slipping. They call those limited slip differentials. And you'll find those usually in high-performance sports cars, in a four-wheel drive, or large trucks to help increase traction to both wheels. The third type of spur gear is rack and pinion. So it consists of a flat straight gear and a circular gear. If we look at this, this actually looks similar to an internal gear set, but we take that internal gear and we cut it and we lay it out flat. If we bent this around as a circle, it would look like an internal gear set. So this rotational movement of this spur gear actually creates a linear movement in either direction, depending on the rotation of the rack. So we call this the rack and this the pinion. Rack and pinion gear sets are usually limited to slower speeds. Now here's a little bit different rack and pinion using a helical pinion, so you can see the slant of the teeth. And we'll be talking about helical gears next. You may have heard over the years that some cars have rack and pinion steering. Well, that's what this is. There's a shaft tied to the pinion, and it's tied directly to the steering wheel, and as we turn the steering wheel, then the rack moves back and forth, and that is tied to our tie rods that are tied to our wheels that turn our wheels left and right. With modern cars, we have a little bit of a different system. We have power steering. We still have a rack and a pinion, but we have some other things that are involved here. So turning the steering wheel does a couple of things. It turns this pinion valve and it actuates a rotary valve. So the rotary valve is taking hydraulic fluid from the pump and it's helping push this piston. So it will go from the pump back to the reservoir, or it will go in the opposite direction in the other fluid line to help push the rack the opposite direction. So it's actually using hydraulic fluid to help push this rack back and forth in here. So if you've ever tried to push a car with power steering, it's very hard to steer. But just start it up and you can turn that wheel with one finger because of the hydraulic ram helping push the rack back and forth. This here is very similar to how your dual acting cylinder works on the trainers that we use in lab classes. But this is actually using, instead of compressed air, it's actually using a hydraulic fluid that flows through here and pushes against the piston. Very same principle as your labs. Now let's take a look at helical gears. So helical gears are an improvement over the first gear type, the spur gear, because the teeth are cut at an angle. You can see how they're angled here and even on here. So more tooth surface are in contact with each other between the two gears. Longer teeth means that we have an increased load and power capability because we have more contact. We can force more load because there's more contact with each gear. We're not just using the small side and tip of a tooth. We're using a lot more of the tooth with a helical gear. Because they're angled, we also have multiple teeth meshing at a time, many more than in a spur gear set. So this results in smoother engagement and quieter operation than spur gears. The angle of the helical gear is called the helix angle. Most systems avoid an angle greater than 20 degrees, but there are some systems that are 30 and even up to 45 degrees. So you can see the helix angle here is the angle off the actual perpendicular axis, or if it was a spur gear, how it is slanted here. And that's the helix angle. Now because these are slanted, depending on the rotation, clockwise or counterclockwise, it will push this gear to one side or the other. So it'll have some axial thrust. So we need to make sure we have a good axial bearing on here, and it's going to push, you can see the slant of the gear, it's going to want to push this gear outwards. To deal with that axial thrust of pushing the gear away, we actually have something called a double helical. So this is actually two different gears, all the same ratio, and you can see their slants are cut in opposite directions. This slants from left to right going up, left to right slanting down. So we have a gap between these gears, between the teeth, and it makes the gear easier to manufacture, although it's more difficult and expensive as compared to a standard helical gear. So both of these rotating cancels out the axial thrust. One is pushing in one direction while the other in the opposite direction. Herringbone gears are another type of double helical, but they don't have a gap in the manufacturing. They are one solid piece. And I actually have an example of a herringbone gear on a shaft that I'll show you during lab this week. These are especially difficult and expensive to manufacture than the double helical gears, but they're stronger and operate well under very high loads and high speeds. So the gear I'm showing you actually came from a large water pump. And I'll show you that during lab class. The next type of gears are bevel gears. And remember when we looked at the differential? That's what this would look like. It would use what's called a hypoid bevel for a ring and pinion on a differential, and we'd have the pinion, which is going to be on the drive shaft, spinning the ring gear. And this would be the carrier, and then the axles would go out through the page up the top and down the bottom. So bevel gears are used when gear drives are needed for intersecting shafts at 90 degrees, like our differential coming off our drive line and going to our ring gear on the carrier. The larger gear is normally called the ring, also could be called the crown gear, and the smaller is the pinion. So that's where we get the name ring and pinion. And we can actually change just the ring and pinion in a differential, which will change the gear ratio. We need to change both because they are a set and we have to have the same diametral pitch. So we can go to a lower or a higher ratio. And you can actually order some vehicles, especially trucks and larger SUVs, with different gear ratios. Let's say you're going to do a lot of towing, a lot of pulling, and you would get a higher gear ratio. This would give you more torque for that power needed to pull a trailer and to get a heavy load moving. And then if you're not going to be using the vehicle for that, well, maybe you would get a little higher or lower ratio, which would give you less torque down at the slow RPMs, but it gives you a faster or higher top end without your motor working as hard. So with bevel gears, we have straight bevel. So they have straight teeth. That is this example up here. They have the same advantages and disadvantages of spur gears because they're really just two spur gears cut at a slant so they will bevel in each other. So speed and gear ratios for a straight bevel needs to be kept low. Now the spiral bevel is like a helical gear. They're cut at a helical angle. They're also beveled, and they offer the same advantage as helical gears offer to spur gearing. So they're a lot less noisy, they provide a much smoother engagement, higher speeds, and increased load capacity on the spiral bevel. Worm gears are another set with non-intersecting shafts, usually again at 90 degrees. The larger gear called the worm gear, that's this here is the worm gear, and then the smaller is called the worm. The worm looks like a hollow cylinder with a thread, an Acme thread. This is an Acme thread example where they're flat on the edges. So worm gears are used to transmit power between non-intersecting shafts similar to the bevel gears. The worm is always the input and the gear is always the output. I've zoomed into this animated picture here so you can see it in action. I'm going to turn it on, and you can see how the rotation of this worm is causing the rotation of the gear. Worm gear sets have advantages. They operate with strictly a sliding contact between the gears. Here's another great illustration of the meshing of the gears. It makes them quieter with less vibrations. However, there's so much metal-to-metal contact here that they generate a lot of friction. So the friction causes them to run hotter, requiring constant lubrication to keep them cool. They handle shock welds low and can have high ratios, up to 60-1. This is huge. They can have these high ratios in a compact area because the worm acts like a thread to transfer the motion like the simple machine, the screw. When we have a gear ratio of 30-1 and up, the worm gear sets are considered to be self-locking. What this self-locking means is that rotation of the worm cannot be transferred to the worm gear. So when we try to turn this worm gear, this is our driven, this is always the driven gear, the worm, the output. And this is always the input or our driver gear. This is the one that's going to be causing the motion to happen. Because of the high ratio, if we try to take whatever is attached to this worm gear and try to spin this worm gear, we won't be able to transfer any rotation or any force to rotate the actual worm in this situation. So when we try to turn this, if we don't let this worm gear turn or put power to the worm itself, then it will not spin. Considered self-locking when we can't spin the gear and cause the worm to spin. Now if we had lower ratios such as 10-to-1, well, we could actually apply pressure to the worm gear and spin the worm. The next thing we're going to talk on is gearboxes. So they have some advantages. And here's a gearbox. It's all enclosed, so it's simple. We have just a gearbox to deal with. Less components and less space are required than other drive methods. The size, they're usually very small and compact. They have high ratios. Belt and chain drives are usually limited to about 7-to-1 or less as far as a ratio. Much higher ratios are possible with gearboxes. They are very versatile. They come in a wide range of shaft configurations, mounting arrangements, and speed ratios. So here we have intersecting shafts. This one is at a certain height above this whole gearbox. This one's higher and it's twisted 90 degrees, and it's going to have a speed reduction in this gearbox. So whatever we apply to this shaft will spin much slower. They're also very low maintenance because they're sealed units. They're easy to maintain and last a long time. If they do fail, they can even be taken apart and rebuilt. Make sure you read through this chapter in your textbook and study the common enclosed gear drives listed, the common gearbox configurations, gearbox installation and maintenance, and rebuilding of a gearbox. You'll need that information to complete this week's homework. Well, that's it for gear drives. I really enjoy talking about gears. They're fun to look at, and I'll be showing you examples of the different type of gears during lab.
If you have any questions after watching this video and reading the textbook, please post them in the Q&A discussion. Thank you very much for watching.